Let's look at a more concrete example about secure update and secure boot. If your firmware is compromised, you are insecure, so you need to make sure you can only run factory-authorized code. A way to do this is when you start use of the system, use a public key signature-based way to make sure your firmware is legitimate firmware. Note that it has to be public key, because any symmetric key approach exposes you to an attack that if someone reverse engineers the symmetric key out of one system, they can fake signatures for updates for all the systems having that same symmetric key. An example from the Federal Aviation Administration shows how this works. The executable code is first sent into the system. But at the factory, a one-way hash algorithm is run to create a cryptographically secure one-way hash. This does not have to be keyed. It can be an unkeyed hash, but the idea is it has the property that it's not practical to change the executable code in a way that will result in the same hash as the unchanged code, that the hash is too unpredictable to make that viable. That hash is then signed using public key cryptography using a private key known only to the manufacturer. In this system, a certificate is also used to make sure that everyone can trust the public key. But in some systems, if you can trust that the public key has not been altered, you don't really need the certificate. You just need to make sure that you can trust that whatever the public key is in fact the public key that belongs to the manufacturer. For example, if you burn the public key into a write-once memory that cannot be changed in a microcontroller, then you don't have to worry that it's been changed. Figure 25 shows what happens at runtime. The executable code and the digital signature are in memory, and the system wants to run. A bootloader inside the system takes the executable code, runs the hash function to recreate the hash. This is not so different than checking a CRC value, except that it has to be cryptographically secure. The bootloader also takes the digital signature, which is stored with the executable, and decrypts it, resulting in a hash value. If the hash value of the executable code matches the decrypted hash value, then you know that the system has an authentic, validated set of code, and you can run the code. This ends up being sort of like a CRC check, where you take the CRC of the executable code and you make sure it matches the stored value of a CRC. But instead of it being a stored value of a CRC, it's an encrypted value of a one-way cryptographically secure hash function, and you decrypt that value to make sure they still match.